Alrighty then, Earth Science students. This code you can't use. I'll put the code up for you, and you can work on this in the meantime, in connection with this lesson. All right. Your teaching point is I'll be able to explain how Milankovitch cycles, eccentricity, obliquity, and precession drive long-term climate changes on Earth, including ice ages. All right, launch. How do Earth's movements in space, such as its orbit, tilt, or rotation, affect the amount of sunlight different parts of the planet receive over time? All right, so you have heard these lessons before. Please pause this video and think about an answer. And when you're good and ready to listen to the answer, you can hit play. All right, so we know that the Earth has its orbit, right? So we have a elliptical orbit with the sun at one foci point of this elliptical orbit. That means that the Earth will experience perihelion in certain part of the year and aphelion in a certain part of the year or a certain day in the season. All right, so one would think that we meaning northern hemisphere, would experience summer when we're closest to the sun and winter when we're farthest away. It is quite the opposite. All right, we experience summer, right, when we are farthest from the sun because the Earth is tilting toward the sun. The northern hemisphere or the North Pole is tilting more toward the sun. That means that the northern hemisphere is getting a more direct ray of insolation, and that is happening at the Tropic of Cancer on June 21st, which is pretty close to us. Us meaning New York State, right? New York State has a latitude that ranges from 40 degrees north to about 45 degrees north. All right, so during the summer season, that's why we experience that. All right, and when we are farthest from the sun, it's still during our summer season, but it turns out to be on a different day, and it turns out to be on or around July 4th, which is Independence Day. All right, on the other hand, when we are closest, we meaning northern hemisphere, closest to the sun, the North Pole is tilting away from the sun, and we're not getting the direct ray of insolation. We are getting some degree, right? We're getting an indirect ray of insolation. That direct ray is striking in the southern hemisphere at the Tropic of Capricorn, which is further away from us, making that winter season pretty cold for us. All right, so orbit and tilt, right? So that kind of goes hand in hand here. When we are closest to the sun, that's around January 4th within our winter season. One thing I wanted to stress to you, and we mentioned this when we had our unit, or at least when we had our lessons on seasons, back in, I think, unit number 3, we mentioned that if you're closest to the sun, it's going to be our winter, but the southern hemisphere is summer. So this being close and far works out right now for the southern hemisphere, not for the northern. All right, when we experience our equinoxes, right, when we experience fall, they experience spring or the vernal equinox. All right, when we experience the vernal equinox, they're experiencing the fall or the autumnal equinox. All right, total opposites of us. All right, and because of the Earth's rotation, in terms of receiving sunlight, um, we have more daylight hours because day and night is evidence of rotation. We experience more daylight hours in our summer. Roughly, we have around 16 hours of daylight in the summer. Like on June 21st, our longest day of the year, we're getting around 16 hours. And that will leave us 8 hours of darkness. More daylight, more absorption, more re-radiation as infrared, making it warmer. All right. On the other hand, for our winter season, all right, we're experiencing less than 12 hours of daylight. So I believe we are getting roughly around 8 hours of daylight on December 21st. And that will give us around, you have 8 hours of daylight, and so that will be 16 hours of darkness. So we have less time of sunlight, less absorption, less re-radiation of infrared, making it colder. All right, there you go. All right, that's kind of the lowdown for this warm up for today. All right, now we got to think about making all these connections that we've been learning about in astronomy and weather, now bringing into climate. Just make these what we call cross connections. Cross meaning different content per se and how it relates to the present day topic. All right, so here we go. Milankovitch, 1879 to 1958. All right, so he has passed. Was a Siberian mathematician, astronomer, and geophysicist. He is best known for the Milankovitch Cycles, which describe how the variations in Earth's movements correlate or connected to climate change over thousands of years. All right, and there he is, right there. Nice tie. Black and white picture, probably a white shirt. Definitely a colored tie, maybe like a red or blue colored tie. Definitely maybe a black jacket there. That's one thing I always like try and figure out when I look at black and white pictures. Like what colors are being shown in those images? Like when I look at the Twilight Zone episodes, I always think about that. All right, anyway. All right, so Earth's movements. Earth is not stable in space. Earth is dynamic. Earth is always moving. All right, Earth rotates on its tilted axis and revolves around the sun. Right? And our moon revolves around us. A lot of gravitational pull all around. All right, so it's affected by gravity of the sun for sure, the planets, and the moon. All right, now we think about the closest planets to us. So Mars is pretty close, but Mars is about half the size of Earth. Venus is almost the same size as the Earth. Venus is also known as the Earth's sister planet or twin planet. But we have our big planets, Jupiter, Saturn, Uranus, and Neptune. Now, Uranus and Neptune might be a bit too far, but Jupiter is relatively closer, being the gaseous giants, the big planets, closest to us than any of the other outer planets. Right, so they have a role, right, in tugging on Earth, perhaps, or having some gravitational effect on Earth. All right, these influences affect the tilt of the Earth's axis and shape of its orbit. I'm going to play this video. It's kind of a lengthy video. It's around 4 minutes long. All right, I'm going to talk through this. All right, how ice ages happen.
Over Earth's long history, there have been dramatic changes to our climate. The ice ages have come and gone. And what's surprising is that there's a strong pattern that explains why ice ages happen when they do. This is called the Milankovitch Cycle. Named after Milutin Milankovitch, his theory explains how the Earth's climate changes over hundreds of thousands of years. His theory is based on two key ideas. First, the Earth's climate is strongly affected by how much sunlight the northern latitudes receive during the summer.
More land
Second,
masses.
This amount of sunlight varies based on changes in the Earth's orbit and rotation. Why are the northern latitudes so important? It's because of ice. When sunlight hits the ground, most of the energy is absorbed as heat. But if the ground is covered in ice, most of the light reflects away because ice is white. This creates a positive feedback loop. Ice forms when it's cold, but ice also reflects light, making it colder, which forms more ice. So ice is really important for climate. The northern and southern hemispheres both contain lots of ice, but there's more ice in the north
growth
because there's more land.
and shrinkage.
Land has a lower heat capacity than water, which means that water doesn't change temperature as easily as land does. This is why coastal regions are generally more mild and why ice forms more easily on land. Just look at the difference between the northern and southern hemispheres. In the south, there are ice caps that grow during its winter, but not nearly as much as they do in the north. During the winter, the land above the Arctic Circle is covered in darkness, experiencing twilight 24 hours a day. It's very cold, and lots of ice forms during the winter. And this is true no matter what's going on with Earth's orbit. The key variable here is how much ice melts during the summer. This depends on how much sunlight there is during the summer. Now, you might think that this doesn't change, but it does. Milankovitch showed that over hundreds of thousands of years, the amount of summer sunlight can shift plus or minus 15%. This can bring ice ages. This can end ice ages. How can the amount of summer sunlight be changing? Well, first, the distance from the Earth to the sun is changing. And second, the Earth's tilt is changing. The Earth's axis is currently tilted at 23.5 degrees. But this changes. Other objects influence the Earth gravitationally, nudging its tilt up and down. Every 41,000 years, it cycles up and down. When the Earth is more tilted, there's more sunlight during the summer. More summer sunlight means that more of our ice melts away. With less ice on the ground, less light is reflected away, giving us a warmer climate. Earth is unusual.
Ooh, that's good. That's good. All right, if there's more tilt, like we had an example during class in which if the Earth was tilted 35 degrees instead of 23.5 degrees, what would happen to the summer and winter temperatures? So that means, if we have 35-degree tilt, that means that our new Tropic of Cancer is at 35 degrees north. And that latitude that's getting the direct ray is closer to us than 23.5. So our summers will be warmer or hotter than normal. And our new Tropic of Capricorn is now at 35 degrees south, which is further south than 23.5 degrees. which would make our winters even colder. Now, flip side. Right, just before we saw the picture of the hold on.
Half degrees. But this changes. Other objects influence the Earth gravitationally, nudging its tilt up and down.
All right, but we had a picture of the Arctic Circle. Now, the Arctic Circle is a number that is subtracted 90 from the tilt of the Earth, which is roughly 66.5 degrees. So on June 21st, right, going back to unit number 3, we learned that the Arctic Circle to the North Pole is experiencing 24 hours of daylight. And then the Antarctic Circle, 66.5 degrees south to the South Pole, 90 degrees south, is experiencing the winter season. Is getting 0 hours of daylight, winter. If the tilt now increases to 35, that means we have a new Arctic Circle line and an Antarctic Circle line. So 90 minus 35 would give us a total of 55 degrees. Yes, 55 degrees. 55 plus 35 is 90. Yeah. So 55 degrees north is our new Arctic Circle. That means that on June 21st, from 55 degrees north to the North Pole is getting 24 hours of daylight. All right, that's a bigger area, getting more daylight, more absorption, and less reflection. And that can definitely melt a lot of ice. On the flip side, right, so on the other side, the Antarctic Circle would be at 55 degrees south. So during the winter, that ice can grow and become bigger and larger. And then when we have our summer for the southern hemisphere, a lot of that can melt because it's a bigger and larger area than what it is now, getting more insulation, more absorption, less reflection, getting warmer. That's good.
And down. Every 41,000 years, it cycles up and down. When the Earth is more tilted, there's more sunlight during the summer. More summer sunlight means that more of our ice melts away. With less ice on the ground, less light is reflected away, giving us a warmer climate. Earth is unusual in that its tilt doesn't change very much. Earth has a very large moon, which stabilizes its tilt. Mars has 2 tiny moons, and so its tilt changes much more dramatically. The next effect is the distance from the Earth to the Sun. The Earth's orbit is not a circle, it's an ellipse. Every 4th of July, we celebrate aphelion, the day that the Earth is furthest from the Sun. Then in January,
this picture is very exaggerated
to the Sun.
It's not like that.
Now the planets Jupiter and Saturn both nudge the Earth, causing its orbit to shift slightly, becoming either more oval or more circular. This happens over a period of 100,000 years. This effect is wildly exaggerated in this diagram. It actually looks more like this. You can barely even see that the distance to the Sun is changing, but this subtle change has important consequences for our climate. Earth as a whole receives 6% more sunlight during January than it does in July. The seasons change because the North Pole sometimes tilts towards the Sun and sometimes tilts away. The change in the distance to the Sun, this works against the change in the seasons. This moderates the seasons in the north, since the Earth is furthest away in July. But this was not always true. The Earth's axis is moving in a circle, It's spinning like a top. This is called precession. In fact, I made an entire video about this. And what this means is that 13,000 years ago, the tilt of the Earth was reversed. When the Earth was closest to the sun, it was summer in the north. The distance change didn't oppose the seasons, it amplified seasons, making them more extreme. Now, warmer summer means more melting. More melting means less reflection, which means the climate as a whole is warmer. The amount of summer sunlight is affected by 3 long-term cycles. 1 changes the tilt. 1 makes our orbit more circular or more oval. And 1 changes how the distance to the sun matches with the changing of the seasons. These 3 cycles powerfully impact our climate. Scientists have measured the history of our climate using ice cores. Now, Earth's climate is complicated. You can't just reduce it to a single input. But the Milankovitch cycles have played a key role in our climate for hundreds of thousands of years. For more astronomical...
All right, let's get some notes down. All right, so we have axial tilt, obliquity. All right. Earth's axis of rotation is not a constant angle of 23.5 degrees from the vertical. That's something that we learn about, I believe, in Unit 3 or 4. All right, this angle can change between roughly 22.1 degrees and 24.5 degrees over a period of 41,000 years. So the Earth, I like to use the term called wobble. The Earth wobbles. I probably will bring this up when we hit upon earthquakes, but we had that one major earthquake over near the coast of Japan. I feel like it was 2011, I think. And it was roughly a 9.0 or 9.1 on the Richter scale for magnitude. And that made the Earth wobble even more. Right? So major earthquakes can make the Earth wobble and begin to change its tilt a little bit. All right, so if we have a change of tilt, that will definitely either make the direct ray closer to us or farther away from us, which can affect our summers and affect our winters, especially for the northern hemisphere, where there are more land masses. Like in the video, it mentions that we have more land mass, and ice can form easily over land because land heats up and cools off faster than water, and especially if it's inland away from coastal areas on top of that. All right, next, precession. All right, Earth's axis experiences a slow wobbling motion. All right, this is known as axial precession. Caused by gravitational forces from the sun and moon on Earth's equatorial bulge. All right, now this equatorial bulge is due to a few reasons. One, this is the true shape of the Earth is called an oblate spheroid. All right, this is very exaggerated, but an oblate spheroid, which is the Earth, the equator bulges out while the poles are kind of pushed together, and this is because of the Earth's rotation. Gravity is pushing down at your poles, forcing the Earth to bulge out at the equators. So we have a larger equatorial diameter, or maybe equatorial radius, or equatorial circumference around, versus the polar diameter, or the polar radius, or the polar circumference. All right, so caused by gravitational forces from the sun and moon on the Earth's equatorial bulge, right? So it's kind of like pulling on Earth in various directions. All right, one full cycle of axial precession takes approximately 26,000 years. Other stars may become the North Star. That's something important. Currently now, our North Pole is pointing toward Polaris. So if we can observe Polaris in our nighttime sky, and you're walking toward Polaris, you know you're going in a northern direction. However, that can change, right, with precession. And I believe the star Vega, I forgot what constellation that's in, would be our new North Star in a few tens of thousands of years. A few thousands of years, not tens of thousands. I believe it's going to be around 13,000 years, I think. All right, gradually shifts the timing of seasons. And in 13,000 years, winter and summer for each hemisphere will occur in opposite points in the Earth's orbit. All right, so we might have a total opposing viewpoint of seasons. All right, in which perhaps when we are closest to the sun, that would be our summer, and the southern hemisphere's winter. And when we're farthest away, that's going to be our winter now, and the southern hemisphere's summer season. Right, a little reverse action from what we know of Earth currently. All right, so this is precession. This is kind of the movement of the tilt going around here, like almost like a cone shaped. I think that's what the precession also will tell you, that it's kind of a cone shape for the northern and southern hemispheres based on the axial tilt of the Earth. So we can have a total reversal of seasons and placement where these seasons happen. All right, orbital eccentricity. Earth's elliptical orbit can change its eccentricity. All right, going back to our equation for Kepler. Eccentricity is distance between foci over length of the major axis. So sometimes planets, right, can pull on the Earth and make the orbit more eccentric, meaning more oval-shaped. Sometimes the pull can be in the opposite direction, in which the Earth's orbit can become less eccentric and become even more circular in shape. All right, circular orbits, mild seasons, small difference in your seasons. More elliptical orbits, more oval shape. This will intensify the seasons, giving you a larger difference in your seasonal temperatures and climate. All right, effects of cycles. Let's finish up with this, and you guys can work on, I think I have 5 or 6 questions right after this. All right, the combination of obliquity, precession, and eccentricity change have major effects on Earth's climate. All right, these changes can be calculated for hundreds of thousands of years in the past and future. All right, so if you purchase that book, these are some pictures inside that book. So you have your Milankovitch cycles of past ice volumes. So we have some increasing and decreasing, almost like a cyclic event, right, that will happen. But this is over tens of thousands of years. right? How we can figure this out through ice cores. We can drill into the ice, and scientists can run some tests and figure out more or less carbon dioxide in the atmosphere. They can even check tree rings as well for growth, or more growth or less growth. So many things involved. Quite a complex thing, right? To really pinpoint like, oh, one thing. It's many things involved. All right, so it looks like eccentricity doesn't have too much of a change, right? But like precession, right? You have your many peaks and valleys over tens of thousands of years. All right. You have the obliquity there. You have your peaks and valleys. Probably not as much as precession. Looks like precession has a higher frequency than obliquity and eccentricity. All right, that's connected here to solar radiation, how much the sun is giving off in terms of radiation. All right, and the most important thing is the northern hemisphere ice volume. Once again, that's important because we have more land mass in the northern hemisphere, and that's where ice can grow and get bigger. All right, and if ice can grow and get bigger, that can be indicative of a potential ice age, or even little ice ages. If we have the ablation, right, or the shrinkage of these glaciers, these big blocks of ice, then we're in a warm period. Currently now, we're in a warm period. Will that change? Sure, it happened in the past numerous times. All right, so we have ice volume. So when you have low ice volumes, probably in the warm period. I'm sorry, millions of kilometers. Okay, so if we have a lot currently, or if we have a lot of ice volume, which is on the bottom, because that's 40 is a higher number, probably have your ice ages. Like currently now in present, right, we have in terms of millions of kilometers, and that's going to be cubed. We are ranging from 0 to 10, probably closer to 0, so maybe like 1, 2, maybe 3 millions of cubic kilometers of ice volume, right? Warm period. But we've had ice ages in the past, numerous ice ages. All right, you have a series of questions, questions 1 through 6. Okay, what are the 3 main components of Milankovitch cycles? How does Earth's eccentricity affect climate? You have your 4 choices. All right, a higher axial tilt, all right, obliquity leads to, you have your 4 choices. Earth's precession, also called the wobble effects. All right, so I know I mentioned wobble before, but you should just connect the wobbling with precession. Number 5, how do Milankovitch cycles contribute to ice ages? And then the last one here, number 6, what happens when Earth's obliquity axial tilt is at its lowest? All right, so please do me a favor, make sure you work on these questions, and that would be it for this lesson. This lesson will be for your next in-class quiz on Tuesday. All right, thank you.